Yeah. Yes. All right. You ready? All right, it is time. It is time to start time variant routing. So welcome and thank you everybody for joining this inaugural session of this working group. As we begin, we're going to start by noting the note well. Again, particularly for those of you, if this is your first IETF, please understand that we are agreeing to follow our IETF processes and policies. Please be aware that any contributions covered by patents or patent applications or owned or controlled by your sponsor must be disclosed. Something that you will see many times in the head of the slides, the next few slides, is that you are being recorded. And these recordings will be posted after the meetings are done. For those of you who are not used to either joining a meeting in person, because this is your first in person, make sure that you sign into the session using MeetEcho from the data tracker agenda, or otherwise there are QR codes in the room that can help get you set up. If you're unsure which of those icons it is, the full MeetEcho experience is the small camera icon. There's also a MeetEcho Lite, which works somewhat better for mobile phones, which is next to it with the icon that looks like a mobile phone. If you want to come to the queue to ask questions, before you come, even if you are in the room, please join the queue. And the way you do that in MeetEcho is by clicking on the raise hand icon. Otherwise, if you are not asking a question online or presenting, we ask that you keep your audio and video off. And of course, if you are in the room, unless you are speaking, we ask that everybody wear a mask because those are sort of the rules here. And I do see some folks in the room who are not yet masked, but as you get set up, please correct that. For any of our remote participants, please make sure also your audio and video is off, and we do recommend headsets. We are all here, so I think we understand the agenda and the resources for Yokohama. And I want to put the agenda up real quick and then pause for a minute just to see if we have any agenda bashing that we'd like to go through. We have a pretty packed agenda in the time that we have today, in the hour and a half. So we're going to finish up with our comments in just a few minutes. We're going to go into a series of presentations. And the goal behind the series of these presentations is to start the discussion on the various kinds of schedule information, where it might come from, what information needs to be present, and how one might use it based on some experiences in other domains. And then at the end of this, because this is the first time that our working group has met, we will be asking for people to consider joining together to author internet drafts, which will eventually become working group documents. Other than that, I am Ed Borain, co-chair. Tony Lee is online, other co-chair. We have Adam as our secretary. And please go into the shared notepad. It's integrated into MeetEcho, and make sure and help us keep good notes. And Adam, you will serve as our Jabber scribe. Excellent. So with that, that's the administrative portion of this. I'd like to turn it over to Tony for just a couple of minutes so that then we can go over some of the really the ground rules of how we're hoping this working group is going to run, and what are some things that we absolutely think are in scope and some things that we think maybe are not. Tony, go ahead.
Thank you, Ed. Next bullet, please. Next bullet.
Well. So that's not working very well at all.
White on white. What a concept.
Well, give me a moment and I'll pull up the slides and share them myself. Let's see.
So we're 2 for 2 right now.
Screen share.
Subsections we've had at the very beginning.
Yes, indeed.
We're on a roll.
Select a window or screen. Share slides. Allow. All right, we have a different set of chair slides. All right, Tony, take it away.
Thank you, Ed.
Okay, well, let's try that.
There we are. All right. So our ground rules are pretty simple. First and foremost, please play nice. Most IETF working groups manage to do this pretty much. We do want to focus on achieving our goals. That'll be our next slide, and then avoiding our non-goals. Our goals are pretty straightforward. We've agreed on making all of these documents, although there was some question about whether or not we're going to produce an informational model. But at least 5 of these documents need to come out. Next slide. Non-goals. So we don't need to talk about every possible use case out there. We really don't care if your satellites are red or blue. It doesn't have any impact on the requirements. Let's not talk about trivia. Let's also try to avoid talking about transport protocols. Lots of folks in NetConf and other places have worked out how they want to get Yang to routers. We do not need to repeat that. And most of all, routing protocols are not dump trucks, probably not the right way to get a schedule to a router. We also do not want to modify routing protocols. That's the domain of other working groups. That's LSR and BGP or IDR. We can certainly take requests to them if we need to, but we probably don't need to. And we will want to recommend behaviors to people, and that's one of the documents that we can write. So, next slide. If you just deorbited and this is your first IETF, here's how to contribute. Write an internet draft. Write it down because we have lots of issues if you don't write things down. Give a presentation and then discuss it on the mailing list. And thankfully, thankfully everybody has stepped up to contribute to this meeting. When we wrote these slides, we didn't have anything. So we were somewhat concerned. But if people don't contribute, Ed and Tony will do everything. And you don't want that. You really don't want that. So, all right. Thank you. Back to you, Ed.
All right. So with that, we can stop sharing, and then I can put back up briefly the agenda and just ask if there's any other walk-on comments to the agenda before we get started. All right. So the first item on the agenda is me talking through a couple of questions around our use case overview. When we started the original Birds of a Feather meeting in London, we wanted to put together a couple of use cases that talked through what we were trying to accomplish and what we thought would be some of the benefits. Now, we're now to the point where we have the working group started, but I think those use cases can still serve as a useful rubric for understanding the kind of work and the kind of solutions we're trying to put forward in this working group. So to that end, I wanted to very briefly, in just a few minutes, go over the 3 primary types of use cases that we had talked about last time. As a reminder, the first was to understand that if we have some information related to when links will and will not be around, then we could do better local resource management on certain kinds of devices. And by managing resources around when we believe we will have connectivity, that would allow for more optimal use of resources on our platforms, which perhaps means that nodes would live longer in the network or be able to pass more data in the network or do more sensing in the network or other functions in the network because they are active for a longer period of time in the network. And that if there is that sense of schedule awareness, this idea of local resource preservation is a potential benefit. And that is a category of use cases. And there are many different versions of that. And as Tony had mentioned, we're not so interested in whether a spacecraft is red or whether a spacecraft is blue. We're just trying to understand sort of the logical benefits. The second kind of use case that we had talked about was how well we could adapt to external conditions, separate from local resource preservation, if things such as our use of power or our access to communication. And the example we had given in London was the case where we might get into data caps or sort of other high rate versus low rate usage of power or comms, then paying attention to a schedule could, for example, reduce the total cost of ownership of running a node or a series of nodes. If we're looking at credits, environmental impacts, green computing, things of that nature, understanding when a high cost versus low cost activity could occur and scheduling around it is another kind of benefit and another kind of use case. And then finally, and what is pretty clearly the major use case for many people when we were talking to folks coming out of the BOF, was this idea of mobility and predicted mobility. And there were a couple of types of predicted mobility. Distance-related attenuation, for example. I drove far enough away that I lost my link. Or external characteristics that we know are going to take away our ability to communicate for a period of time, such as I drove into a tunnel that didn't have repeaters in it, or that I'm planning to change the topology in some way that helps me perform my functions, like I'm going to point my antenna somewhere else for a certain period of time. And all of those, in some way or another, we categorized under the use case of mobility and mobility in the devices. The question that we have to the working group, maybe the first question that we have to the working group is, having captured those use cases, and of course there's refinements to those, is there value in saying that an informational product of the working group should be a statement of these are the driving and non-duplicative use cases that we could use to help shape the work that we are doing? And so I wanted to pause for a moment, and I guess even if we're online, we can still do a hum, right?
We've got the tool, so just use the tool.
We could use the polling tool.
Unless you want to hear us hum.
So if I were to start a poll right now that says, please raise your hand if you think that we should create a use case document as an informational product out of this working group, and do not raise your hand if you think we should not, and that its utility is over. Okay. And I see that Mark is in the queue.
Marc Blanchet. I like use case informational documents if they go clearly into the actual requirements and stuff. Sometimes we see in the IETF, I don't know, 100 pages of use case informational document that, go nowhere. So if it's, to the point and useful for, real work, then it's fine. But so I would have said raise and no, non-raise depending on, the outcome.
So fair and noted. And to say that if we did do an informational RFC, it would still go through a working group last call, and we would still make sure that it was a concise and useful document. But there seems to be a pretty clear consensus here, 41 versus 1, that 42, that we should do that. All right. With that, one thing that I would ask is consider, as you read this document, whether we feel that there are use cases that are missing. If so, what is missing? And also to the mailing list, please volunteer if you would like to help work on this. A use case document that comes through the working group review that has multiple authors, in my opinion, is a useful thing. So please consider volunteering for that. All right. With that, then what I'd like to do is move on to our next presentation topic. And that is going to be Emery. So Emery, are you online and can you hear us?
I hear you.
Can we hear you? Yes.
Hello, hello.
Yes, we can hear you loud and clear.
Excellent. So, howdy all. My name is Emery Annis. I'm actually giving this brief on behalf of Brian Sipos. He was unavailable tonight, but he's a colleague, and I can say I could agree with everything that's in these set of slides. this is to give a little bit of a background on what is the Aeronautical Information Exchange temporality model. There is no actual IETF draft today associated with this, but it's sort of to bring to light an existing time variant information model that exists in the community. So I'll kind of walk through and talk a little about what this is, what it's not, and how we might apply it if we were to TVR. Through this set here. So Ed, next slide. Or I don't know if I can forward. Great. So just a little background as to sort of what we're trying to do here. So effectively, this temporality model came about because in the aeronautical industry there was a need to convey time-based, schedule-based information. They needed a way, a common language that allowed people to convey that information so that everyone understands what was being conveyed, what are the bounds on that information. So that is exactly the use of this model. It provides for both absolute time and periodic time. And one thing that's very important to understand for this model, it's completely abstract from the producers of the information to the users of the information. So what I mean there is this is strictly the information model for conveying the state of a system or a feature to a system, a property of a system. It does not attempt to prescribe why that state changed or what caused that state to change. So it's strictly a model to describe the states as a function of time. Some of the things to note down at the bottom, right? It's kind of the inverse to what I just said. And also, this is an information model for a different industry. It's not necessarily prescriptive to TVR, but something to think about because there was a lot of work that went into this and a lot of lessons learned. So next slide. All right, so just a little bit more background, and also the link to this temporality model is at the very bottom. So I highly encourage anyone to go read that. It's actually very well written. As a baseline, so Axum is actually a huge model which is comprised of many different components. You know, if you love UML and want to go read about all the different components that are even applicable in the aeronautical industry, it's out there. This temporality model is a separate piece. So it evolved from the need to simply convey that time variant information, and they wrote it as a totally separate document and standardized it as part of Axum. So it kind of speaks to the importance that they saw that for this information model. Its original intent was to convey these notice to air mission information exchanges, NOTAMs. These are things that effectively, either planned or something immediate has happened, and they need to send out a notice to the community to make the aeronautical community safe or just actually operation as intended. One interesting thing to note is even though it hasn't been standardized in maybe some of these other communities, this concept has been used as a link planning tool for ships, cruise liners who are actually connecting to GEO, MEO, LEO satellites. So I think that's some motivation, kind of going back to the use cases Ed mentioned, that this is actually applicable to this community. So move forward. So to kind of set the tone to what this is, and like I said, go read the document. It describes it probably much better than I will. One component that this is conveying are features. So first off, a feature could be something like in this picture of a runway. You could imagine the state of a runway could change over time. Maybe it's only valid or allowed to be used between 8 a.m. and 10 p.m. every day. And also properties of that runway might change. Maybe the direction of the runway might change. Maybe the frequency with which you would talk to air traffic control to use that runway might change over time. You can imagine that these are planned well in advance to support all the users of that runway. So this is a model that allows you to express that information. So like I said at the top, a feature sort of describes all of the properties, P1 through P5 in this picture, of those time variant things that are changing. And allows you to kind of specify what are the bounds on those properties. When does it start? When does it stop? And what's the state on those properties? So next slide. Some definitions, these are pulled straight out of the Axum document. I won't go too deep here. The one thing I guess to note is this model supports both permanent definitions of state over time as well as temporary state. And I'll go into that on the next slide a little bit more. So go ahead. All right, so here's a picture of kind of pulling it all together of the different sort of time states inside this model. You can see you've actually got a baseline. So when you define this this model from the beginning, they call it a baseline, and you define all of the properties associated with the feature. You define your start of life as well as your end of life, and you can see how there's clear, discrete boundaries between each of the state changes in this picture. You also have the ability to specify temporary values. So that's your temp delta. So maybe an emergency happened or something failed and you want to express the ability that there is something temporary. It's not part of your long-term model, but you have the ability to specify that. You can also update your actual baselines with what they call perm deltas. One thing that's nice to note, if you look at the Axum model, is the language describes conflict resolution, if you will, for this model. So it applies, I think, sequence numbers and basically another number that allows you to, if you've got several of these stacked together, you know what is the most current, what is the most accurate set of information, and how to overlay these different slices to know what is the state at this very specific time. So go forward. So there are a couple of things. Sorry, 1-4. Okay, so one very important piece to this model, which we think is actually quite useful to TVR, is the ability to specify periodic behavior in your schedule. So you could imagine for a vehicle that's it's an IoT sensor that's driving by maybe every day or maybe every few hours it moves past a sensor and it needs to close that link. You could specify that here. Now, one of the nice things of allowing for sort of periodic representation of this information is it's compressible. It's easy to convey without having to specify every single change forward in time. You can specify these periods at different durations. I think the one caveat is that they should not overlap, right? It's very nice to kind of express that up front. So move forward. So two things that this model doesn't capture, which might be very useful to TVR if something like this were to be adopted. Number one, parameter interpolation. The idea here is an Axum temporality model. Everything is very discrete. Those parameter values are discrete, but we could imagine a use case where latency in a comms link changes as a function of time, or maybe the pointing vector of an antenna as it's steering changes as a function of time. So looking forward, it might be useful to be able to express those parameters as a function of either time, position, or some other input parameter, rather than as a discrete value. So this was something that might be useful to add to a model like this. Go forward. Another concept not discussed in Axum is sort of a planning horizon. So Axum simply describes how to express information and transmit that. In this community, we might have a need to only look forward a little bit in time. So if I'm a device who's consuming this information, even though I've been expressed a model that moves on for many days or weeks, my time horizon might be very short. So an ability to differentiate that from the information which is being conveyed might be a useful concept to alleviate the burden on those devices that are trying to consume this information. But this would be not necessarily a part of the data model, more a part of the, going back to Ed's use case, a use case that allows you to use that information different for different users. Go forward. So bringing it all back, like what are some of the use cases here for TVR? Well, you could very much imagine this concept of expressing parameters over time, very true for a router or a communication system whose link varies over time. You would be able to specify when those changes are occurring and what's the state of the system at those changes. very useful because this gives the systems which are consuming this information, it gives them the ability to decide how they consume the information. As the model is only useful for describing the information, it allows the systems to actually use that however they need. And I think the last bullet here, periodicity, very important possibly for this community. So last slide. So the conclusion, and I would say the takeaway for myself, from Brian, go read this model, check out the concepts that are there, and perhaps if we are starting to describe a data model for TVR, see if there is a way to utilize some of the way that information has been expressed in Axum. I think could be a very useful concept, a nice language that we can use to discuss the terms of applying a data model or use cases in this picture. Take a look at it. Lots of lessons learned, and yeah, I would say use the forums to see how it works.
All right, Embry, thank you very much. We do have a couple of people who have joined the queue. George, please go ahead.
Just a quick question, is this model freely available to be used, or we have to deal with the FAA and the European agency, to be able to grab pieces of this model?
So this, I think on the second slide or so is a link to the model. It's a standard published by the aeronautical information or the aeronautical industry. You're free to use it. There is no content in the model. It's simply a language that describes how would you convey this information and how would you specify the state as a function of time or periodicity. So there's no real information that you would be using inside the model. So I would say it's free to consume, look at, and leverage.
Next.
You mentioned something like following antenna as a function, as opposed to, I guess, a table of values. So I was wondering, is there a good worst case example what you're seeing right now where Axiom doesn't do it well with a table, and if so, why doesn't it include functions? Because I think that, as you mentioned, might be very interesting for TVR, and I wouldn't know how to decide whether we would need functions or just tabular representation.
I would say there is, I guess it depends on how, are there discrete steps in time, or is the granularity so small that you would have 1,000 over a period of, say, a minute or a couple of minutes, 1,000 different states. And if you've got to that granularity, expressing the function sounds way easier. But I'm sure the details need to be worked out as how you would know what is the state as a function of time. How do you negotiate that time or position or whatnot, to be determined. But they simply have not done that. Theirs is very discrete sets of parameters.
But they do have use cases where they're following antennas, like from a ship or something like that.
Well, let me just in the interest of time, I know that we have a lot we have to do, get into the 90 minutes. If there are questions related to what are the capabilities of the model, let's please take it to the mailing list once we've had a chance to look up that model. Stuart? Same one. Oh, okay. And Q?
Hi, Q. Michael, you mentioned the concept of processing horizon, as in at what point would it no longer be beneficial to consider data beyond this? Does the Axiom model contain support for signaling what might be a useful processing horizon, like, beyond this point the data is more of a gas, or is this not defined?
Today, I think it could be, if you look at the model, it has both the sort of language to describe it as well as examples using UML and examples of how you would convey that information. So could you add this as a field? Yes. Now, I think one of the pieces, though, is potentially this should not be part of the information model because each device might decide how they are to use that separately. So a configuration parameter of the device, not necessarily a useful component of the information which you're going to convey.
Yes, but is there information that the device could use to make its own determination of what it might consider a useful processing horizon?
Oh, I'm sure. Absolutely.
Okay.
Emery, thank you very much. Our next presentation, the use case of the tidal network. The presenter, Li Zhang.
Hello, good afternoon, everyone. I will introduce time variant scenario in the tidal network. Firstly, we know the tidal effect is very typical on our network. For example, in the couples network, there are thousands of people go to the teaching area and go back to the dormitory at different time. And the picture on the right shows the fluctuation of the traffic at different areas, such as the teaching area and dormitory. And the migration of the students generates a lot of traffic and lead to the fluctuation of the traffic. And another example is the Chinese New Year. We know that about more than 200 million people move from their work town to hometown, and they also generate a huge of traffic on our network. So also the device consumes less energy when it has those data, but the energy efficiency is very low. So it is an effective means to shut down some links or nodes when the traffic is low. So based on that, there is a time variant scenario in the tidal network whose links or nodes will shut down or power on in a specific time. Okay, next slide. We have some assumptions and routine paths in this use case. Firstly, we assume that the regularity of the tidal traffic is predictable. We need to know when the traffic will increase and when it will decrease. The second assumption is that we need an algorithm to calculate which nodes or links need to be shut down or needed to be powered on at different traffic scales. And this use case also has some routine paths. Firstly is the data model with time variant information. For the time variant information in the tidal network, it always has a regular period, but it may have multiple regulations. It means it will have many periods, many start time or end time, and so on. Yeah. And the second point is the connection and advertisement for the time variant information. The nodes the nodes may to advertise its own time variant information to other nodes, so that each node in the network knows the whole time variant information about the topology. This may be not necessary if the controller already knows all about the time variant information. And the third one is the routing algorithm based on time variant information. Because if a routing computer already knows about the time variant information, it can do some measures before the change of the topology. For example, it can quickly compute a new path before the change of the topology. Okay, next slide. This page shows an example of the network demo for the dormitory. The network consists of 4 nodes and 6 links, and the picture on the right shows the regularity of this network. We can shut down link L6 and L5 when the traffic is low to save energy, and we can get 2 topologies at different time. But still, we have some problems to be solved. Firstly is how to describe the time variant information. It may be complex, as I have said, it may consider of multiple period, multiple start time, and multiple endpoint. But it is with a predicted periodic characteristics. And we also may need a new algorithm based on the time information, because if there are some packets being transmitted on the link, the shutdown of the link will cause some packet loss. Okay, that's that. Okay, that's all. Thank you.
Thank you very much. That was a large amount of information in a short amount of time. Do we have any questions? All right. Thank you very much.
Thank you.
Yeah. Our next presenter is Scott Burley, who will be giving us a brief history of contact graph routing.
Can you hear me?
Yes.
Okay, good. My name is Scott Burley. I'm going to be talking about contact graph routing, which is a time variant routing mechanism developed for what ultimately turned into delay tolerant networking. And I'm going to, in this presentation, talk about the origins of that mechanism. Next slide. This all goes back to the original motivation for delay tolerant networking, which was extending the internet into interplanetary space. And how would you do that? And there are various constraints on deep space mission communications that are that inform a lot of the characteristics of contact graph routing. First of all, in deep space mission communications, there are no wires, of course. There's no cables out to a spacecraft. Everything is wireless signals, either radio or free space optical. The distances are potentially very long. Between, here in Mars, for example, is between 3.5 and 20 light minutes. So over these long distances, you get high signal attenuation over wireless transmission. So the data rates are reduced by the distances, and that also sort of precludes omnidirectional transmission, because that further reduces the data rates for power that goes into the transmission of the signal. So links between communicating nodes are formed by directed transmission between antennae that are pointing directly at each other, so that you maximize the received signal power. So the other characteristic of long distances is that you have high latency over the links, and so client-server kinds of operations are contraindicated. In particular, like connection handshakes, terrible idea over a 40-minute round trip time. So negotiation in particular is kind of off the table for the protocol design. Next slide. The second sort of class of characteristics is that the capacity of the transmission is constrained. The transmission reception rates are limited by aperture size. You have large antennas on the ground and small antennas on spacecraft, and available power. You have plenty of power at a ground station, minimal power at a spacecraft. So the data rates to the spacecraft from the ground and from the spacecraft back to the ground are likely to be very different. They're highly asymmetric. You also have a small number of ground stations on Earth, which is rotating, so they're not always pointing in the same direction. And they're supporting multiple spacecraft, which are in orbit, either in orbit around the sun or in orbit around some other planetary body. And spacecraft antennae are usually, not always, but usually body fixed. So in order to point the antenna, you have to point the spacecraft, and that isn't always possible because the spacecraft has potentially instrument operations that demand that the spacecraft be pointed in a particular direction that is inconvenient for pointing the antenna at the same time. So what this all comes down to is that signal interruption is routine and sustained. That is, connectivity between a ground station and a spacecraft is virtually never continuous. It's usually alternating, punctuated. Sometimes the opportunities for transmission are separated by intervals of hours or days. Next slide. What this amounts to is that mission communication capability for a given mission, for a given spaceflight mission, is limited, asynchronous, episodic, expensive, precious. The way to think about these opportunities for transmission is that they are temporary instantiations of a physical layer medium that come into existence when the ground station and the spacecraft antennae are pointing directly at each other. Pointing a ground station antenna at a spacecraft is called tracking. When you have one of these opportunities to transmit, it's called a tracking pass. And you can think of a tracking pass as being functionally analogous to an Ethernet cable that is, once in a while you plug it in, and then a little bit later you unplug it. It's a physical medium that comes into existence and then goes away. Mission operations people initiate tracking passes by commanding the movement of the ground station antenna to point at the spacecraft, and commanding the maneuvering of the spacecraft to point at the ground station. And they do this according to a schedule that coordinates the commanding at both ends. And the document that records that schedule, which is a file that gets passed around to the ground stations, for example, and transmitted to the spacecraft in some way, is sometimes called a pass plan. Next slide. So here is an excerpt from the pass plan for the Ulysses mission that was exploring the poles of the sun 12, 15 years ago. And you see at the bottom, these are the tracking passes that are scheduled. The GBOT is the ground time beginning of the track. The GBOC is the ground time beginning of being able to command to the spacecraft, and so on across the line there to the spacecraft event times at which the communication begins and ends. This is a fairly routine sort of document for operating a spacecraft, operating communications for a deep space spacecraft. Next slide. The communication at Mars is similar, of course, but it's actually more complex because it was determined a long time ago that the communication from a rover on the surface of Mars is, you can get a lot more data from that rover if the data from the rover is relayed to an orbiter instead of transmitted directly to Earth. This is maybe counterintuitive, but the reason for that is that the orbiter can be, because it doesn't have to land, can be much larger than the rover on the surface. And because it can be much larger, it can have much larger solar panels, therefore a much more transmission power, and it can have a much larger antenna. So the bulk of data from Mars landing missions for the last 15, 20 years, I think, has been by means of transmission from the rover to an orbiter, which is very close, and the data rate can be pretty high, even though the rover's got a small antenna. And then transmission from the orbiter back to Earth. So there's a relay discipline that manages high-speed return of data from a Mars mission. Next slide. And so corresponding to the pass plan we saw for Ulysses a couple of slides ago, this is a graphical representation of communications plan from MAROS, the Mars operations relay operations system for planning operations of orbiters pointing at rovers, and then alternatively turning and pointing at Earth. Next slide. So what we did with in dilettante networking thinking way back when was generalized the idea of a traffic pass into contact, because in some cases the communication we wanted to be able to do would be time varying, but wouldn't necessarily involve tracking with a ground station. And a contact plan then is a list of contacts, a representation of the time varying topology of a dilettante network, a list of all the communication opportunities between nodes. It's a schedule. It can be distributed to the affected nodes long before the contacts begin, which is what makes it possible for it to be accurate at the time it is invoked. It's managed. It's not discovered. So this is authoritative. It's going to be the contacts that are in the contact plan are commanded. They're not opportunistic. It is managed knowledge of the physical topology of the network. It is the known communication connections between the hosts and the routers. In the same way that connections between hosts and routers in the internet are managed knowledge of the physical topology of the internet. So next slide. For example, here's a really simple network. It's got 4 nodes in it. There's communication between A and B, between A and C, between B and D, between C and D, but none between A and D. If you wanted to route between A and D, you have to send it through a relay in B or C. Next slide. And a contact plan governing the communication over that little network could look something like this, that there'd be a contact starting at time 10:00 for an hour at 1,000 bytes per second, as with A sending to B and B sending to A. And then at the end of that, there'll be another contact between B and D, where B is transmitting to D at 1,000 bytes. It's another hour of that, and D is likely transmitting back to B, and so on. Next slide. So you can imagine taking that information and representing it in a graphical way here, where we've got the same physical topology being shown, and the time dimension of that physical topology. It's a time variant multigraph showing the episodes of connectivity between the nodes. And next slide. This is actually, in a sense, the same sort of thing that we get with a picture like this. In both cases, what we're looking at is the physical media connecting nodes of the network. It's just that in this picture of the internet, the physical media are up all the time. It's not time varying. They're pretty much always operating. Next slide. So contact plan, if you look at it, it may look a little bit like a routing table. It's not a routing table. It's a map of time varying network topology. It can be expressed in a graphical way in the same way as any other network map. It just isn't always, because it's convenient to list it as a list of contacts instead. It doesn't have any routes. It only identifies what are functionally something very much like lengths of fiber optic cable. It's that knowledge of the time varying network topology that contact graph routing uses to learn the routes between nodes in the network, in the same sort of way that knowledge of the physical internet topology is used to learn routes between internet nodes. A route from one node to another in a DTN network is a succession of physical layer instances of transmission media, that is contacts, in the same way that a route from one node to another in the internet is a succession of lengths of optical fiber, Ethernet cable and Wi-Fi and so on. Next slide. So that brings us to what contact graph routing is. It's a way to use the information in a contact plan to compute routes. And we do that by projecting a contact graph from the plan, a contact graph being a directed graph of a subset of the contact plan. It contains all and only those contacts that are components of a path from a given source node to a given destination node. And once you've got that directed graph, you can use Dijkstra's algorithm to find the shortest path from the source node to the destination node. And that's what contact graph routing is. Next slide. So here, for example, is a contact graph taken from the same contact plan from a few slides ago. And the graph is kind of counterintuitive in that the nodes are not the nodes of the network. The vertices of the graph are the contacts themselves, and the arcs connecting the vertices are periods of retention of data at the node that is the tail end of the previous of the earlier vertex and the head end of the receiving vertex. Next slide. So there are routing tables. Contact graph routing will populate a routing table, but the routing table coming out of contact graph routing is a list of complete routes, not a list of next hop neighbor to use for all of the destinations that are in a range of addresses. And it needs to be for a couple of reasons. Since each transmission opportunity is very limited, it's irreplaceable, expensive, utilization of every contact is important, and some bundles may be too large to be transmitted during a given contact because contacts are finite, and sometimes a bundle in the bundle protocol is too large for transmission over a contact, either because it's larger than the absolute size of the contact, or it's larger than the residual capacity of that contact because other things are already queued up for transmission using that same contact. What you do for every bundle in contact graph routing is find the shortest usable route that you can send the bundle on. If there is no such route, then you have to compute a new one by doing another Dijkstra search through the contact graph. If you can't find another route, then the bundle is not routable. It has to be discovered. Next slide. When you enqueue a bundle for transmission on a route, that restricts the volume of transmission opportunity that's available on that route, which has two effects. One is it limits the volume of bundles of bundle data that can be forwarded on that route, so you may have to switch to a different route. It also increases the delivery latency of bundles that are queued up for transmission on that route. And so even if the route is usable, it's no longer the shortest path. And so in both of those cases, you have to switch to a different route. And that you may end up ping-ponging between a couple of routes. In effect, what you do may amount to load balancing the routing of data so that you're maximizing the utilization of every contact while still ensuring that every bundle reaches its destination before expiring. Next slide. Contact graph routing was introduced in 2007 when the initial release of the Interplanetary Overlay Network software came out. It was used to conduct the Deep Impact Network experiment in 2008, which we operated an 11-node network that spanned about 15 million miles. It included the Epoxy spacecraft as a BP router at a distance of between 50 and 80 light seconds from the rest of the nodes of the network. It has been, contact graph routing has been operational on the International Space Station since 2016. It's currently supporting the Korea Pathfinder lunar orbiter spacecraft in orbit around the moon. It's the basis for an international standard, the CCSDS scheduler bundle routing standard 734x3b1, and an alternative method of using contact plans to compute routes that uses that does not use contact graphs, but instead uses node multigraphs. Potentially more rapidly has been proposed. It's still the basic idea of using contact plans still it matters, but
So Scott,
the way you
if
use it,
I could interject in the interest of time, though, would this be something that we could maybe present at a subsequent TVR working group meeting?
Sure, absolutely. And this is my last slide, so we're good.
No, thank you. Thank you for that history. And as we mentioned before, understanding and seeing how various use cases our operational systems are working is important. In the interest of time, I'm not going to take Q questions for this right now. If we have some time left at the end with open mic, please come back then or put your question in the chat. All right, with that, we're going to move on to our next set of slides, which is forwarding in time variant routing. And our presenter is Marc Blanchet.
Konnichiwa. Next slide.
Yes.
Here's the rationale of the work. Well, we know now what space communications is about. Motivation is that I'm currently developing a bundled protocol stack in Swift for Apple platforms and also Linux. The aim is to get bundled protocol apps on for example, an astronaut iPhone. We'll see. So questions came up about policies regarding holding, dropping, forwarding bundles. As you may well know, in one sentence description of bundled protocol, it's a store and forward system, right? Or layer 3 system where you store bundles when you don't have connectivity or reachability to the destination until, reachability come back. For example, when you have a link, then you forward and it goes over the network. So it's really a stored forward. So I looked at different BP bundle stack implementations that are roughly available as open source. Variable support to policies regarding what you do when you hold or you drop or you forward bundles, including a lot of to be done. No easy way to specify various behaviors. So the proposal or the purpose of this draft is to actually specify policies to what to do in forwarding. For example, and you will see in the next slides, when storage is full, priorities, when reachability is restored, stuff like that. While it's becoming from BP, I try to generalize it for IP. We'll see if that flies. And obviously the data model could be modeled in Yang. And for the purpose of this presentation and the document and the next presentation, I'm using packet instead of saying packet or bundle, because depending on which layer 3 you're using. So I'm using packet, but think about bundle at the same time. Next slide. So forwarding behavior. If the destination is unreachable, the packet is not discarded and therefore saved in memory. That's the basis of bundled protocol. Whether it's volatile or non-volatile is an implementation decision. The packet should be saved with a timestamp to be used by policies described later. When a new route is installed, or in general, when the forwarding table has changed for whatever reasons, then the saved packets are parsed, quote, quote, parse, and those that can be sent are sent in order of preference policy discussed next. Next slide. So therefore, policies are needed for following events. Packet memory store is full or bundle, and a new packet is coming. What do? Do you accept that packet? Do you drop some packets to have space for that packet or bundle? A destination becomes reachable by a new route entry in the forwarding table. Which stored packets do you forward first? Some descriptions of what Scott was saying previously. Sometimes the window opportunity is so small, bandwidth may be small, so actually you may not have time to forward all the stored packets you have. So you have to decide which one you would send first, right? A packet has expired, do you start with that or, do something else? The capability of storing packets for a forwarding node may be resource demanding, especially in scenarios where resources are very limited, such as space. Therefore, the forwarding node owner may want to have preference on which types of packets are stored or not. For example, I may say that I have a policy that stores packets based on the source address or destination address, or in the bundle world, node IDs and endpoint IDs, or various fields such as flow label, listservs, or else, right? And bundles have the same similar kind of fields. So that can be used for defining policies for forwarding or dropping packets. When packets needs to be dropped, an error should be sent to the source. Both IP and BP has those error messages. However, in a constrained environment, error messages may be too costly to send back to the source. Or another case is just that the packet or the bundle is just too old. There's no need to send an error message back because it's completely irrelevant anymore. So, think about space where, it may be an hour, a day before it actually comes back, or a week or something. So there should be a policy to tell the forwarding node what to do in terms of sending error messages back or not. Next slide. So drop policies, a list, an enum of them, could be more or less. Drop the oldest, like FIFO. The last one from these sources, which are defined. So for example, I prefer that the packets or bundles coming from my organization or these kinds of sources are very important compared to others. So I define, drop them the last, drop last for destination, or drop last if there's a field as some value, diff serve bit or something. Error messages policy is essentially send or do not send error messages. Or it could be if send error message only if it's not too late, and those two are orthogonal. Therefore, you can have both, one drop policy and one error message policy. Next, forwarding policy. Remember, the link is back. I have reachability. What do I do? Which packets or bundles am I forwarding first? So forward first from these sources, for these destinations, or if a field is set to a value. Next, and I think that's mostly done. Tony, so some comments I received. Tony was asking why IP. So some use cases are actually where the delays are not too much, but still requires time variant routing, and there's many discussion about that. We'd need a Yang model, so actually move that text description into a Yang model. Should we have weighted multiple concurrent policies? For example, for this destination, this, and for the other, for the sources, like complex set of policies. Do we need a default policy that could be defined, and obviously define the IP and BP headers fields that could be used for policies. Next slide, and I think that's the next.
And then after that, we do have one person in the queue.
Sure. And so looking for working group adoption, that's the specification, and looking for more comments.
Speaking of looking forward to comments, we have one comment. Rick, go ahead.
Hi, thank you for this, Mark. I hope you can hear me. I like the work. I have a chair. I chair the DTN working group. So if this is deemed out of scope for TVR, we can take this in DTN. The reason I say this is I think a lot of people will look at the IP properties of forwarding and say, actually, we've studied this. We have good policies for this that have covered us for the last 20 years, random early drop, etc. I know this work is very relevant for bundle protocol. So if it's deemed out of scope for TVR, we'll bring it to DTN, or you and the chairs of both working groups can discuss whether this is the right place to go. I'm kind of open to suggestions from the floor or the group here, whether actually TVR wants to grapple with this. If not, DTN can happily take this. It's in scope of our charter as well.
And again, in the interest of time, since this initial meeting is the starting of exchange of ideas, let's please take those opinions to the mailing list. We have one more person in the queue, Eric.
In the interest of time, I could take it to the mailing list, but I'm deeply skeptical that this will be very good for IP. But not at all skeptical that it will be great for bundle protocol. I think it would be so.
Right. We do have one more real quick, Ron, if you go while we're queuing up the next set of slides.
Hi, I'm Ron Feld. Do you foresee this also supporting opportunistic routing? Because there's a lot of work out there already. Protocols like epidemic, spray and wait, Profit, which is even an experimental RFC.
Well, let me jump in on that and just say, even back from the Birds of a Feather meeting, we had said that was not one of the things that we felt was in scope for this working group.
Strange, but okay.
Yeah. But we can take that for sure to the mailing list. Okay. Now we have Mark, who will be talking about a contact plan for time variant routing.
Konnichiwa. Next slide. Same slide here, running a bundle protocol stack, looking at contact plans and looking for what the others were doing. And I've seen everyone has a different contact plan format and model. So I was like, oh. So I suggest that we standardize this data model and file format for a contact plan. Again, while coming from the BP side, generalize it for IP. And that would enable contact plan people, engineers, to actually have a single format. And then, whatever the implementation is actually used. Enables comparison, diffs, revisions, archiving, all kinds of stuff that, if everybody has a different format, we're not going anywhere. Next slide. So this is the example. It's encoded in JSON. So essentially an array of contacts. Each one has an ID, a UUID for a family. This slide shows IP family. Source, list of destinations, next up. Start time, stop time, bandwidth, latency. I have a few comments on those. So V4, V6 examples. Next slide. And then on the bundle protocol, there's two URI definitions, so DTN and IPN, and those are essentially similar. They are, some of them are actually taken from one implementation, but converted to that format. Next slide. So comments received, Dean and Tony, please use Yang. Agreed, we'll do next rev. Dean has offered to help on that. Tony, unnumbered links should be supported. That's a good point. I haven't looked at it. YIP is actually something which was for the other document. Tony was providing a good comment. Should we have instead a top-level ID field and an index for each record? I haven't thought about that. There's pros and cons of this approach. Having an ID on each record enables editing and removing, adding new stuff on that record without changing all the indexes. So there's pros and cons. I'm not sure yet. Maybe we should have an ID on both levels so it supports all possible things. Next slide. Support empty list of contacts, Tony. Yeah, sure. Why list of destinations? Tony again. BP doesn't really have a way to specify a prefix like an IP, so it has to be a list of node IDs. There's some ways to do wildcards and stuff, but so I think we will need a list of destinations so that if the contact record is the same but for different destinations, then you only have one line. Why, Tony, again, why start and stop mandatory? That's the current model. I agree, which is probably only one is needed. And I'm not sure about none because then there's no time variant portion of it. Tony was saying, bandwidth and latency. Why? The bandwidth is actually specified in BP implementation, so it's actually imported from that. Latency was my own because I want to help the transport to know what's the latency, but I know it's a later layer evaluation, so maybe we should just drop it. Felix Walder, maybe we should have for the DTN part, the convergence layers index. Agree, we'll do this next.
We also have one person in the queue, Rick.
Do
you want to take it after?
Yeah.
Okay.
I think I'm done almost. If you're Rick, you can wait. Scott Burley said no need for this file format. Disagrees on. Scott, please come to the mic if you disagree on my summary of your comments. But so data model is useful. File format may be up to the implementer. I could agree with that. So then that's sort of a link to what people were saying previously. Starts with a Yang model and see, the encoding. Phoenix Walder specify properties such as the probability of contact. I've seen this in some BP implementations, but I was not sure what to do with it. So, maybe. Next slide, and I think that's the last one. Yeah, so thanks for the early reviewers. Looking for working group adoption and more comments.
All right, thank you. And Rick, go ahead.
Hi, Mark. Thank you for that. I owe you a proper review on the list, I know. One piece of advice, having implemented similar things in the MANE world, the ability to split the metrics away from the individual links is useful. The ability to say, here are some sets of metrics that are common across multiple of the links. It makes the model a bit more manageable. And my second point would be being able to have dynamic sets of metrics, because for some operations, and again in TVR, we're trying to be fairly generic here, some operations bandwidths are relevant, but some metric we can't think of right now may be vital for that deployment. So being able to maintain some flexibility in what an individual metric is, but have a common treatment for that metric within the model, I think is a really wise thing to do. And I would support adoption for this. I think it's got lots of work to do on it, which is fine, but I think it's heading in the right direction.
Thank you, Rick. So summary of your second comment is essentially make most parameters optional so you could fill them out later, right?
All right. Mark, thank you very much. And our last presentation today is Luis, who's going to talk about using Alto to expose time variant routing information.
Thank you. Next, please. Yeah, well, the rationale of this draft is essentially based on the motivation of TVR which is about the predictable changes, so modifications in nodes and adjacencies and so. So the consideration from a network operator is that probably these changes could be scheduled from a higher level system like OSS or network controller or so. So this is more focused on these situations of preserving resources and so, or even schedule maintenance changes and so. So we can expect that they will be scheduled somehow from this OSS or these network controllers. So because of that, because there is some plan for these changes, so the impact of these changes can be somehow calculated beforehand. So maybe we can consider that there could be algorithms embedded in the network controller that could calculate what will be the impacts of the changes that are foreseen, or maybe we could even consider experimental ways of retrieving the expected new situation, maybe playing with network digital twins, something like that. So there will be at the end means of understanding what will be the impacts. So then, because we will be able to have both views, the present view and the future view, then we could use that views for exposing all those changes to applications, so external applications. And here is the point where there are existing IETF solutions that can assist on such exposure to applications in order to inform those applications what will be the changes, the future changes. Next, please. So Alto is one of the solutions from IETF for that purpose. Well, on your left, you can see a potential, let's say, architecture. There will be multiple implementations. So maybe the Alto could be connected to the digital twin, or maybe the digital twin could not be in the picture and everything being done in the network controller. The importance of the figure is essentially to understand what could be, let's say, the flows of the information and how we'll consume the flows. So somehow from the network controller, we could feed the impacts in the Alto server. The Alto server could expose those impacts to the application. The application, through consuming the Alto information, will be aware of those future changes in the topology, in the routing. And then in some point in time, the network controller will act on top of the network for introducing those changes. So this is more or less the rationale of the figure. So Alto defines in RFC 8896 a calendar cost. So somehow it's able to expose the present view and future views in terms of cost metric, right? So essentially, Alto provides a view between PIDs. The PIDs are aggregator of prefixes in the network, and Alto is able to associate metrics. One of the metrics is the routing cost. So through this calendar cost view, we can build this evolution or those impacts of the changes that are scheduled for in the routing in the network. No? So the Alto cost calendar introduces a number of attributes. For instance, the calendar start time, which indicates the date at which the first value of the calendar will apply. The time interval size that defines the duration of an Alto calendar time interval. The number of intervals, and another parameter for repetition of intervals, and so on and so forth. So somehow, Alto is introducing a number of parameters that could be relevant for TVR. Next, please. So regarding the discussion on the usage of Alto for TVR, so Alto enables the exposure of TVR information to applications, because we can expose both the current and the future situation. So here would be of interest to assess if the exposed information that Alto provides reflects the problems that are proposed in tailored TVR problem statement, which are changes in nodes, adjacencies, and so on and so forth. So trying to understand if that kind of information matches. A second point could be the fact that Alto cost calendar defines a number of time-related attributes. So here the point would be to analyze if such attributes are sufficient for expressing the TVR or the time variance nature of the routing changes in TVR. Third point would be that the expectation in the problem statement draft is to extend existing routing protocols for conveying TVR information. So here the point would be to define how Alto can participate in of the routing processing of this new information that could be generated for TVR in such a way that can process directly instead of maybe connecting to the controller or retrieving from the controller. And finally, the data model or models that could be defined in TVR could be leveraged for Alto for that purpose, for understanding the changes and digesting the changes that will come. So next, please. So the chairs asked me what could be the relevance of this draft for TVR, and I identified two possible ways of relevance, or two possible points of relevance. No, one is the attributes that Alto considers for handling these schedule changes. So probably those parameters could serve as input for TVR at the time of defining the info and data models. So somehow Alto can consume the TVR information. So probably having in mind these attributes could be useful for the definition of the info and data models. And second, the Alto cost calendar can be considered as an additional scenario of usage of TVR. So it's a kind of TVR use case, or at least we can understand like that. Behind Alto, we will have a number of applications like CDN, gaming, XR, VR, whatever, consuming those changes in the topology. So somehow it's a kind of umbrella of multiple cases that could consume this time variant routing information. So the next steps for this is basically to collect feedback from the working group and to identify work that could be in the scope of TVR or even in the scope of Alto for further development. So that's all from my side. Thank you.
All right. Thank you very much. Okay. So if we were to go back to the original slides, the share slides, which perhaps will show what we need them to show. In the last few minutes, one of the points that we wanted to make is that the goal behind the discussions and the presentations today were to try and understand what are some of the cases where we have operational systems or pre-existing work that is trying to deal with schedules, whether they are spacecraft schedules or airplane runway schedules or network traffic configuration optimization schedules, to try and understand where there are commonalities in the various use cases, ConOps, data models, implementations. What we have to do as a working group is turn these sets of experiences into drafts, and in particular to call back up the list of working group items that we must produce. And here are our milestones, starting at the bottom, a problem statement and use cases, which we have, and as we sort of voted on earlier, having an informational use case document is something we want to do, followed by requirements, an information model, data model, applicability, and statements, and then considerations. We probably don't need to work on all of those concurrently, right? There is a dependency between some of this information, but what we do need are people that are willing to volunteer to start working on some of these things, rather than having dozens of individual internet drafts that are competing with some of these ideas. Or competing with each other for ideas. Perhaps the first thing to do is go to the mailing list, start identifying who is interested in working on what pieces of this problem, so that we can start getting folks together around consolidated internet drafts around some of these ideas. So that is my request. And please, we start putting together this material, is take to the mailing list where your interests are in contributing in these various milestones, and of those who are of like mind to solve the problem, to start collaborating so that we can start getting internet drafts for the next IETF. Otherwise, what we can have now is just maybe, I know that there were some questions that came up prior when we were having some of our other presentations. We can open the mic now for just a few minutes if there are any other comments or questions that didn't get in from before. And I see one already. Dean.
Hi, Dan Bogdanovich. So from the information model is more or less already somewhat defined, and based on Mark's document, because we have some examples, and the data model, the initial basic data model can be refined out of that. And there will be a lot of optional requirements, but for the basic requirements, I don't see that many, that big of a required model that it has to be, because the basic thing is what I've seen in all of them is the calendaring option that is added to the path option, and then you have different types of what path you can define. Is the physical layer, data link layer, or is it the ADIP layer? So that's the one, but the use cases are pretty well defined for space area. At least what was, from what was presented. It would be more interested to see some of the terrestrial use cases for the TVR and be able to use that, from those use cases further on.
Thank you. And agreed. And we have Stuart.
Hi. Go to that one. Stu Card, AX Enterprise. So I may have missed it, but what I seem to find missing from much of the discussion is the concept of probability. Schedules, calendars, et cetera, are predictions, and predictions have associated uncertainty. And so the limiting case on one end is when I'm very, very certain, because it's only 1 microsecond into the future, and thus highly predictable, and I can treat it as if it were 100% certain. And then on the opposite extreme, you have the kind of opportunistic stuff that Ron was talking about. Do we anticipate having any kind of explicit representation of the confidence or probability, as you wish, that our calendars and schedules will be correct, or ways of dealing with the situation when they prove incorrect?
Again, agreed and so noted, and something to discuss on the list. Lou
Berger. I think the last person was just hitting on something that was really bothering me or been thinking about is I think we don't understand all the link attributes that we need as part of the schedule. And I think a speaker earlier said maybe we need some ability to do opaque attributes so we can handle future ones. But I think this is an area that would be really helpful. I don't know if it's in the use cases or the requirements, is to better understand what kind of attributes we need to create our time variant routing schedule.
Heard and very much agreed. And an example of that is when we have talked through a contact graph, if you have a platform that has multiple radios and you say that I have a link between 2 different nodes, how do you know which radio is providing that link? And that may be important information. All right, with that, we have 3 minutes. My readout is simply to say I think our high watermark was almost 100 people who joined both in person and online. This is clearly something that for which there is a lot of interest, and we will maintain that interest because we will be active on the mailing list. We will coordinate on internet drafts. We will proceed against some of the things that we're talking about here, and we will see everybody in just a couple of months. Please, again, for the goals, the things that we are trying to focus on is to make sure we understand the requirements and the information models for how we would use this time variant information. And I'm looking forward to some terrific discussion on the mailing list. Tony, is there anything else you'd like to say to read us out? And if not, then what we can say is we can even adjourn 2 minutes early. I'm not sure what the probability of that contact would have been, but thank you all so much.
By the way, you can use that one if you want to have fun. Okay. And if you need some help.
Yes, I think that's fair, and as it should be.
I replied back to your email, but I never heard back.
It should be. Just look at. I have immortalized it. It is time.
No, that's fine. I was like, I said reply back, and then like radio silence. I'm sorry, yeah. No worries, all good.
This was very well attended.